Welcome to video 5 reinforcement learning on the grid. So throughout 4 chapters we built machines that predict, that see and that create. But every single one of them has been an observer. It looks at the world and describes it. It never reaches out and changes anything. Now we cross a line. Forecasting can tell you a storm is coming and the wind will die at 6 o'clock. Useful actually, but someone still has to decide what to do about it, isn't it? Fire up the gas plant now, or wait, discharge the battery, or save it. Ask a few thousand homes to ease off for an hour. That decision made again and again, and this is the world of the agent. This is called reinforcement learning. So the reinforcement learning has one core picture and it is a loop. And the agent observes the state of its world, it takes an action. The world responds with a new state and reward a single number saying how good that was. Then it goes around again. Put the grid inside the loop. The state is a snapshot like this. Demand generation, the flows on each line, how full the batteries are, the price of power right now. Likewise, the action is a lever. Charge or discharge a battery, open or close a switch, shed it or not, and the reward is whatever you care about. Money saved, emission avoided, and above all else, the grid staying inside its safe limits. The agent has exactly one ambition: choose action that pile up the most reward over the time. And that phrase over time is where it gets subtle. The reward is usually delayed. Charging a battery costs you right now and only pays off hours later when prices spike and you sell it back actually. Greedy agent chasing only the immediate reward would never charge at all. So the agent learns to value the future. We add up all the rewards still to come, with later ones discounted slightly. A reward today is worth a little more than the next week. That running sum is called the return. The agent's job is to learn how much total return it can expect and which action earns the most. Q-learning does this by nudging its own estimates towards reality, a little at a time. Over thousands of rounds, a strategy emerges that nobody ever wrote down actually. The cleanest place to watch this work is a battery. Across a day, prices rise and fall, and solar and wind surge and fade, usually. Well-trained agent learns a policy that sounds obvious and is anything but. As you can see in the screen, charge when power is cheap, clean and plentiful. Discharge when it is expensive and scarce. Now do that not for one battery but for thousands of flexible things at once. Home batteries, EV chargers, water heaters, air conditioners. Coordinate them. And you flatten the demand curve and you can see the shave the evening peak, and this is called demand response. The problem environments like CityLearn were built to train agents on. Now, the hard application is they are operating the high voltage grid itself. When transmission line starts to overload, operator can reroute the power. And opening and closing switch happen and literally change the shape of the network. The number of possible configurations is astronomical. And nobody can hand you the single correct move. You cannot label it actually. You have to discover the good strategies by trying them out and seeing what keeps the light on. Which is why France grid operator RTE built a simulator called Grid to Org and launched public challenges named Learning to Run a Power Network, Explore Safely, where a mistake costs nothing. And this is not just a simulation. So, DeepMind and Google famously use machine learning to cut data center cooling energy by around 40%, and later handed an AI system control of that cooling directly. So AI already runs real energy systems today. But operating a live transmission grid is not the same as cooling a building. It's totally different. You train your agent in a simulator where it can fail for free, then you deploy on real infrastructure where one bad switching action can cascade into a blackout. The real grid always differs from your simulator. That is the same to real gap, simulation to real. So the frontier is not chasing move reward, it is safety, hard constraint, human in control. So we have finally given a machine the power to act on the grid. But in every chapter we keep flattering the grid into flat list of numbers. And in doing so, we discard the one thing that makes a power system a power system. How it is wired together. Grid is a network, literal graph of buses and lines. What if our model could respect that structure? So that is called graph neural networks. The next video we will meet you. Thank you for hearing me out.